So why are you dealing with log plots in the beginning? So it's because it's mathematically much more convenient because you are lazy. The control engineers are very lazy, actually. It's not actually true. And then let's see, let's make a very simple example, which is 1/s. And then for here, to make a frequency response, we can simply plug in j omega. Then it becomes gj omega becomes 1/j omega. The magnitude, angle is not that hard actually. So the angle of the system is -pi/2, so it's not that hard. So angle is not a big issue for this case. Well, what about the magnitude? Let's write here. What about the magnitude? Becomes 1/omega. So, and what this plot looks like. So the angle plot is again, it's not that hard. It's -pi/2 for entire phase. But the magnitude, now it looks like something like this. So it's very hard to know what's going on, especially for the high frequencies. So one solution for this is taking log. So now, if you take a log for this magnitude, it will be log 1/omega. Then it will be log 1 minus log omega, and becomes minus log omega. So what it becomes, now it becomes simple linear line. So this is much easier to draw and interpret the system, even for to identify system ID. So that's why you are looking at the log system instead of the looking at the pure magnitude. And even further, for typically there's a called decibel, which is log magnitude times 20. So we also multiply 20 to these systems. And then just like it's multiplying the 20 to a log magnitude. And actually this makes the system draw, this makes for us to draw the log magnitude plot much easier as well. So now what you can do is that for the log magnitude plot only, we know it'll have something like this, but typically we are looking at for a small frequency, low frequency, which can be omega equals 0.1, then 20 log 0.1 becomes 20, right? And when omega equals 1, 20 log 1 becomes 0. Log 1 is 0. And then omega equals 10, 20 log, actually, should be negative 20 because it's 1 over x. Minus log omega. Plus 20, 0, and then 10 becomes my negative 20. So then we can draw the log plot in a little bit more the precise way. Let's see. So around omega equals 0.1, the magnitude is about 20 for the system, and the omega equals 1, the magnitude is 0, and the omega equals 10, the magnitude is negative 20. So it'll have, so we know this will be, the plot will be line. So that will be something like this line. Say this is 20, and then this is negative 20. And then the slope here is negative 20 decibel because log 20 log magnitude is decibel. 20 decibel and the per decade. So this is in log magnitude called decades. So it's much easier to draw and understand the system by taking log in the angular, the frequency, as well as the magnitude. That's why we are taking the log. And then also log has several good properties, such as the multiplication becomes addition. This is very important. So it means that if you have something like this second order or first third order system, it can just simply becomes the multiplication. Let's say you have s plus a. And if you take a log, then it'll be log 1 times s plus a inverse and s plus b inverse. So it means that it becomes log 1 minus log s plus a minus log s plus b. So all of a sudden, all the multiplication becomes simple addition and subtraction. So it's one of the main reasons that I like the log plot. And it's linear, it's a powers of 10. And then as I just showed, the inversion is becomes just negative. And then gain 0 at the when gain is equals 1, if the input and output is the same, the gain becomes 0. This becomes very important towards the end. So the example I showed before here, this is a zero line. Means that up to this frequency, the input, if we give jiggly input, even though there's a phase delay, as shown this phase plot, and this is a magnitude plot. There may be phase delay, something like this. The magnitude will be the same. The input and output magnitude will be the same. So that's the meaning of the 0 decibel from this log characteristic. Then now let's look at the simple system, such as G equals K. It's a simple magnitude. So 20 magnitude of this G is 20 log G J omega is 20 log K. So this is constant because there is no variable of the omega. And then the angle becomes the K is 0 degree, and so becomes it's 0 degree because there's no angle. So for this K, then the this Bode plot will be as simple as let's say this is magnitude, and then this is angle. And the magnitude will be this, this axis is log omega. Will be simply 20 log K. And then angle will be 0. Where if gain K is zero, larger than 0. What about something like this, first order system? What do you think? So we just look at the first order system just before, which was 1 over S. And then because that, this can be written as G J omega equals A J omega plus A, and in the root complex plane, we are looking at something like there is a poise here, and then looking at the angle depending on this all these angular frequency. So what you can immediately see is that for angular velocity is too large, omega equals 0, the angle, the change in angle is almost 0, and the magnitude will be the just 1. It's like this magnitude, and when the omega equals becomes negative infinity, the angle becomes almost 90 degrees. And around this angle, where maybe I need to draw in an opposite direction. About this angle, the angle becomes about 45 degree, like about here. So, and magnitude is 1 over j omega. So 1 over j omega means that this is the magnitude. And then inverse of this magnitude, let's say the magnitude is A, and then 1 over the A, inverse of the magnitude, is almost approaches to 0. So this is something we are expecting to see in the log plot, this Bode plot as well. And then here is more detailed derivation of the first order system. So again, let's say GS equals, let's say 1 over S plus A. Now I even get rid of the A. And then again, the frequency response is plug in j omega to the transfer function, means that it becomes this, and then j omega becomes the magnitude of this becomes omega square plus a square, omega square plus a. Yeah. So it becomes omega square plus a square. And the angle is nothing but minus arctangent omega over a. So what you can get from here? So from the magnitude, so let's look at when omega equals very small, very, very smaller than a first, and the omega equals almost the same as a, and the omega equals larger than a. The omega is very smaller than a, then from the magnitude equation, from the equation 1, the omega part is almost negligible. So the magnitude is almost becomes 1 over a. We can also see this equation from the original equation. If the omega is very small, it's almost the same as a. Then from the equation 2, the angle, also if the omega is very, 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 very small, the angle becomes almost 0 degree. And the omega is almost the same as a, then magnitude is 1 over a square plus a square. So it becomes 1 over root 2, the 1 over a. And angle becomes arctangent a over a is negative 45 degree. And when the omega is much larger than a, now the a is negligible. So the magnitude is almost the same as 1 over omega. And the angle is almost the same as arctangent negative omega, means that negative 90 degree. So from here, what you can get is that for the magnitude, 20 log omega, 20 log G part for the omega is very, very smaller than A, the magnitude is 20 log 1 over A is negative 20 log A. And for the case of magnitude, omega is almost the same as A is, in the case of omega is almost the same as A, magnitude becomes 20 log 1 over root 2, 1 over A. And then thanks to the log characteristic, it's very hard to, easy to calculate. It becomes minus 20 log A minus 20 log root 2. And when the omega is very, very larger than A, now the magnitude is just function of the omega. So magnitude becomes negative 20 log omega. And then the angle is also, regardless of the angular angle, it looks like this. And about the omega in between, here the angle, omega is like, it's not that smaller than A and then not that larger than A either. The angle becomes actually this angle. This angle. And then we can calculate, we can draw Bode plot. Really, using this characteristic. So now we need a ruler. And then let's have x-axis is log omega. The y-axis is decibel, which is 20 log omega. 20 log magnitude. So we typically have a line for this is typically we have a line for. So 1, 2, 3. So even let's have the outside of this scope. 4. So this is typically with the smaller, smaller and then same and then large. And then this becomes even very smaller. So if it's 10 times smaller, it's considered as it's very smaller. It's very smaller than A. And then at that point, the magnitude is negative 20 log A. So so at this point, well, this point is almost negative 20 log A. And then when it equals A, that becomes something like this. Magnitude is even a little bit smaller. Like here. And when the omega is large, now it has even smaller than like negative or log of SQRT2. Then when omega is larger, then it will decay very quickly with 20 decibel, depending on the omega. So what it happens is that about here, it looks like this. And about here, it's like decaying slightly. And the y as the omega becomes large, it will decay very quickly with the slope is negative 20 decibel per decade. So this will be the magnitude plot. And then for the phase plot, when omega is very small, the angle is 0 degrees. So let's say this is 0 actually. And then it will be 0 up to this point almost. And then when the omega is the same as the A, it will be negative 45. And when the omega is very large, then it will be negative 20 or negative 90 about here, and it will stay there. So the magnitude plot will look like something like this. So this will be the magnitude plot, or the phase plot. Then this will be the magnitude plot. We can do the similar thing for the second order system.